think it's working. All right, shout out Tana Russo. Hi, Anna. Hey, Anna. Hey, Bodhi, I hope it's treating you well. We miss you, I know.
I love you.
I know. Thank you. So, so today's lesson is, I think it's more just the idea. It's kind of like a breakthrough lesson. Once we get this one, I think the rest will be easier to get. I feel like I have a lot of pressure today to explain this very, very well. So I'm a little nervous, but hopefully, fingers crossed, I got this.
You're gonna do great.
Oh, thanks, Jesse. I'm thinking a kid. Oh, you're a kid. You give me a little voice of confidence. I'm a little nervous about this lesson. It's so hard. Thank you. You are my superstar. Because he's so nice to me. Okay, so that's one in my heart too. Oh, I love it. All right, so today we're going to talk about the limit comparison test. And so you guys are learning some new convergence tests today and the comparison test. One of these I think will be a cakewalk for you. Other one, I just have to explain it really well. But first, before we do that, I'd like to do a review problem. So just, it feels weird because you guys have had to do a lot of this learning on your own, I feel. So, so example one, let's talk about the infinite series, the square root of 1 over n. So let's guess. What do you guys think? Convergent or divergent?
Divergent.
Good, very good. Why?
Less than 1.
Okay, that's what I wanted to hear. So we can take the square root of 1, and this is into the 1/2 power, and that's a p series. That's right. So really, these are going to be a really fundamental part of our convergence test. I hope these become very automatic to you. If p is less than 1, then what happens to my series? Diverges, yeah. Or equal to 1. And then if p is greater than 1, so if we have like squared to the 3rd power to the 4th, it converges. All right, so just, I don't know, I just wanted to hear you guys know that that was p series, right? We're good at that? I'm just assuming that you're cool. So now, let's do example 2. Square integral, sorry, not integral, the infinite series sine squared n over n squared. Convergent or divergent, what do you guys think? Give me a guess.
I thought it was convergent. I thought n squared was. I don't remember.
Convergent.
I'm hearing both.
I don't remember.
Don't remember. C or D? Well, I don't know. I don't hear a real unanimous answer. So let's try and figure it out using some tests we know. So let's do the divergence test. Always try this. Always try that divergence test. The limit of the nth term. What's the limit of that? 0. So does that prove it's convergent? No. No, 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 no. It's inconclusive. Inconclusive. We can't use that test. So here's a problem. So this is inconclusive. 2. It looks sort of like a p series, but it's not, is it? You have to have, so this 1 over n to the p, and you can have a coefficient, you know, it can be 4 times that or 8 times that, it's still a p series, but you can't have a function in the numerator.
Is there no way to do like a comparison?
Yeah.
Oh, that's what we're doing.
Yeah. I want to walk you through this flow chart. Exactly. You guys, yeah. DH Yoda. Woo, ready? Good. So smart. Yeah, exactly. I love the way you're thinking. But you guys, a lot of this for me, just like when you had to figure out which way to solve your integrals is kind of like a flow chart, I think. So is this. You have to kind of weave your way down through things you know how to do until you hit on something that works. So divergence doesn't work. It's not a p series. It's not a telescoping. It's not geometric. Always think about these things, though. Nope. Nope. Not telescoping. That's when we have like a fraction minus a fraction, and then you can pair up and things subtract. Yeah, I think, oh, and then you guys know the integral test. That always works. What's wrong with the integral test for this example, though?
Because you don't have the inverse sign in.
Yeah, this is a tough integral. It's tough. It's possible, but it takes a long time. Yeah, it's not fun. It's like integration by parts, and yeah. I mean, if it's something's going to take you a really long time to take the integral, there are better ways. So even though if you can find the integral of this, and you can show that the integral of this as a function converges, then you can prove that that series converges. It takes a while to do that. So we're just going to cross that off, cross that off. So this is all I think you know. I don't think you know anything else, right? That's it. So, oh, and it's also not, yeah, it's not steadily decreasing, so that doesn't work. So we need a new test, and just like Jonah said, we're going to do a comparison test. And this is very similar. Do you want to see that one? Thank you. Sorry to ask you. So the comparison test is very similar to the comparison theorem you guys did with integrals. So I don't think this will be too big of a stretch. So these are all no-go. But I think it's good to think about those. So the idea for the comparison test, just like the comparison theorem with integrals, is we're going to find, let this, and I like to do this because I hate writing all that stuff all the time. I'm just going to say let this series a sub n equal my infinite series. So I can just write this. You don't have to do that, but that's my habit. So we're going to let this, this infinite series be this series a sub n, and we need to find a similar series that we're going to compare it to. And what we really need to do is we have to guess convergent or divergent, and we have to guess right. So what's the value of the numerator? Now remember, n are positive integers. So, well, yeah, and then even this is something weird because what makes we don't include 0, so we can get 0, but can we ever get 1 here? Because you need pi over 2 or 3 pi over 2, so we're not going to get those. So the numerator is always going to be from 0 to 1 in that range, and then we have this n squared in the denominator, and then it's okay, yeah.
1 over n squared.
Yeah. Yeah, it's a p series with p greater than 1. So we're going to compare this. We're going to guess convergent, because you have something that sticks to 0 to 1, and this is getting huge. We're going to compare it to this series b sub n, which we're going to say is a known convergent p series. You can use those anytime. This is a known convergent p series. And say that. This is a proof. Tell me what you're comparing it to, and that this is that converges, and how you know that. It could converge because it's a geometric series. It could converge because with the absolute value of r less than 1, or it could just be a convergent p series. So now, just like the integral test, what we're going to do is we're going to say we're going to compare these two, and we're going to compare the terms of this to the terms of this. I want to show all these terms are going to be smaller than a known convergent series. Yeah? So this is like kind of step 1, and then step 2, you have to compare terms. If you're trying to prove that it's divergent, you have to show that it's larger than a known divergent series. In this case, we're guessing convergent, so we have to show that it's smaller than a known convergent series. So we're going to do, we need a sub n to be less than all the terms b sub n, and greater than root to 1. And natural numbers.
Can we not do a sub n is less than or equal to?
Or equal to, yeah. Yeah, sorry, thank you. So, well, that's not so bad, because this is actually a very easy test, because this term, sine squared n, so because you might want to just say, because the range of sine is from 0 to 1, this numerator is always smaller or equal to this numerator. So thus, this is smaller than a known convergent series. I'm running out of room. Do I write all that? Probably should. Since sine, I have a kind of small board because I'm filming today, so since sine squared n is less than or equal to 1 for all n, a sub n is indeed less than or equal to b sub n. And then your final concluding statement should say, by the comparison test. You need to tell me which test you're using, either in the beginning of this proof or at the end. So by the comparison test, and you can use this shorthand, the series a sub n converges. Or yeah, I love QED. That's what I had to do. We both quote errata demonstrandum. You're not supposed to do both. I'll just do QED. So it's a proof. Do you guys believe it?
Yeah.
You convinced? Yeah. Okay, good. So now, no, this is the easy part. Oh no, you're joking. I'm glad. So here we go. This, we're done. You can put a big check. It's this one, limit comparison test. I don't know. So now, example 3. N equals 1 to infinity of 4n squared plus 1 over n to the 4th plus 1. So I'm not going to do this every time. I'm kind of just doing it today because this is kind of new. But what I'd like to do, guys, is go through all your options to show whether it's convergent or divergent. So this is the last time I'll do this. But you should be doing it in your head. So what's your guess? Yeah, good. You can get a king. You were a little shy about it, but you're the only voice I heard. Thanks, Alice. Guess C or D, convergent. Okay, earlier in your candy, what made you say convergent?
Because the bottom term is a higher exponent.
Yeah, very good. Oh, you totally deserve that. Awesome. Yeah, so, you know, as n gets infinitely large, this 1 doesn't matter anymore, does it? And it really starts to look like as n grows infinitely big, we get this 4. It's almost like this becomes 4n squared over n to the 4th, because plus 1 is so small when you're talking quintillion or whatever. So this just becomes like 4 over n squared essentially, which is a known convergent p-series. All right, so now that's a good guess, and it's a correct guess. Alice will totally get credit for that one. All right, so we'll just know. No one else spoke up, so now let's go through our test to prove it. So in our heart of hearts, you guys are all pretty convinced that that converges, right? But now we have to show it, and we have to prove it convincingly. So, okay, I always go to the divergence test. You should too. It just takes a second. You don't always have to write it down, but let's take the limit of the a sub n term. And what do we get? 0. Inconclusive. No good. So it's almost like a p-series, but it's not, because really the p-series, we can't have a function in the numerator. So 1 over n to the p, that's no go. It's not a times r to some n. It's definitely not that. It's not telescoping. It's just not going to work there. The integral test, when I thought of this example last night, I'm like, it kind of looks like maybe you can tweak this with arctan, because we have like something squared plus 1. And I'm like, my teacher in tuition told me, I don't even know if this is possible. You know, some are not possible. So I went to, I wasn't going to do it. I went to Wolfram Alpha, and it's like this long, and it's log, natural log, and so many arctans. And not only would that take you like an hour probably, I think, to like break up the fraction, and I mean, it's kind of cool to think about, but, and not only that, but then you have to take the limit. And remember on your test, you had to take the limit, and then you got L'Hopital, you had 0 times infinity. So do you see that this could be a huge pain? Oh, we're not doing the integral test. That is off the table. It would work if it has an antiderivative, but it's just too hard. Yeah?
Can you split it up and do comparison?
Yeah, well, let's do
four?
comparison then. Let's do the comparison test right now. So these are no good. So let's try the comparison test. So we're gonna let, for ease, find so we guess C, convergent. So our B sub n, what's the logical choice for our series B sub n? Yeah. Uh-huh. Is that okay? So now we have to compare. So yeah, so this is a known convergent p-series. So what I need to show is that all these values have to be smaller than all these terms. So does that work? It's not going to work. I mean, first off, this is like, you know, I could factor out this 4 and then make this 1/4, and these don't matter, but still, this is 4 times as big. It's not going to work.
Oh, so that is what I was saying.
Yeah, so the comparison test, it's not, you have to show without question that every single term is smaller than a known convergent series, and this doesn't, it fails. It's not that it's not true, it just, this test doesn't work for us. There are lots of tests. Oh boy, you guys, there's so many tests. So now we need this one, this limit comparison test.
Wait, can I?
Yeah, I mean, I know. Can we talk about it after though? Is that all right? Because I know where you're going and it's valid, but not easy though, right now. Okay, I know. So here we are back at square one. So now time for a new test. Thanks for your patience. So limit comparison test. So the way this works is, actually, I think probably should just give you the formal. So what I'm going to give you the formal definition of the limit comparison test. Then I'm going to explain it in my own words, and then I'm going to show you why it works. So it's not pretty when you see the. I think the book is awful, by the way, at this section. Are we on? I think so. So I think the book is really bad here. So I'm glad you guys are here. And it's one I'm filming too. I don't think it's easy to teach this yourself. So the limit comparison test says we're going to let a sub n and b sub n be series with all positive terms. So that's required for this. And then it says if we can show that we're going to take the limit as n goes to infinity of the nth term of what I'm trying to prove divided by this series I've chosen to compare it to. And if that value is between infinity and 0, not including 0 or infinity, if it's a finite value, not including 0, then it's saying that these two series behave similarly, and whatever this is doing also. So it's saying, if this is true, then you can conclude that the series a sub n and b sub n behave similarly. So if your suspicion was this diverges, you would want to choose a divergent series to compare it to, and if you get this result, you've shown that it's divergent. If you decide that this is convergent, we have to choose a convergent series that's similar to this. And okay.
Why the a sub n over b sub n?
Hmm?
Why do you have the a sub n over b sub n? Like why does that
I mean, you can do the other way around too. It's okay. There'll still be a finite value, but it's kind of what's standard in the book. So.
No, I just mean that I missed.
No, this can be b sub n over a sub n. It's okay.
Not the question.
It doesn't matter. What's the question asking?
Let's continue also.
Okay. So, yeah, I'm gonna erase this. And yeah, I think I'll go right into the proof of why this works. I'm gonna erase this. I'll put this back up on the board because we gotta talk about why this works. So. Okay, so let's assign this value c to that center part of the proof. It's going to be the limit. So we're letting c equal the limit of this as n gets infinitely large. Now the test says if the test works, you get the c between 0 and infinity. Okay? Yeah? So this is the result we want. We want a c that's not 0 and it's a finite value. So now, do you guys agree with me? If there's a limit, if you think about what's going on, we have these dots, and we're approaching that limit c. And remember what I talked about the epsilon, the plus epsilon, minus epsilon? From that, there's like a band after some n, where all your terms are going to be within that band. So I'm going to call this top end m and this lower band m. So we're going to say, okay, I know it looks a little ucky, but this is this is a really beautiful proof. I just recently learned this. The proof in the book is awful. So do you guys agree with that? Think about that one. Think about it hard a little bit.
And M and M are arbitrary.
Yeah. Exactly. So there's this band of values that the limit, all the terms are going to be when they get close to that limit. M is going to be that upper bound. Because it never approaches that value c, but it's super close. Right? Okay, is that good? So now, we let c be this. Okay? So now, we're going to say that this is the limit as n grows infinitely large. I'm going to say so as as n grows big, these are the same. Good? Okay, now watch this cool trick, because we established that we have to only use positive terms. This is important for this test, that all the terms have to be positive or else this won't work. I'm going to multiply all, you see where this is going. I'm going to multiply this by b sub n. So I'm going to multiply by, so I'm going to get b sub n times m. So this is crazy. It's crazy. It's saying if you chose a divergent series, this term is smaller than that divergent limit. If you chose a convergent series, this is larger than that limit. Now this is only true, this is really important, that this has to happen. All bets are off if that didn't happen. None of this works. 0 doesn't work. I'm going to show you an example where I get 0, and maybe you'll see, this does not work for a lot of infinite series, but it's going to work for that example I just had up. So over here, I'm just going to show you, let's say you have this series. You don't know how to deal with this yet. 1 over e to the n. Now that converges without anyone's doubt, right? That is really fast moving. But let's say you let this be your a sub n, and then because you don't have a lot of choices, let's say you compare it to, and I'm just, for the sake of simplicity, I'm going to say a p series. And because that's so big, I'm going to do n to 1,000. That's big enough. It's not. So when I do this limit comparison, can I erase this? Are you guys okay with this? Oh, yeah, sorry. Yeah, thank you. So what this is saying is, if b sub n, this series b sub n was a divergent series, you've shown that all the a sub n terms are larger than the terms of a known divergent.
Wait, but why is that side divergent?
I'm just saying it works both ways. Depends on which one you chose.
I just mean, why is that side
divergent.
Well, it has to work out that way. Like, if, I mean, this is the, remember the lower band we talked about?
So the fact that it's a lower band?
Yeah. So, I mean, it's funny, like, it just works. Like, if this is a divergent, this is going to happen. This falls between values of B sub n.
I just don't
depending
get
on the
why
range.
you can assign that B sub n times
Oh.
small n as divergent and B sub n times big N as convergent. I get the, like, it's in between them and you can decide whether it's convergent or divergent.
No, that's a good question. I mean, this is just, I think, kind of, this is not a super robust proof, I think. But this is just a basic idea. Like, the robust proof is indisputable, but it's complicated.
Do you have any explanation on why that's?
So, I mean, no, not a very good one. Like, if it's divergent, this will be true, and that's not a very good explanation. No. Let me think about it for a little bit and come up with a better one.
Creating two different functions there, I mean, not functions, series. Like with the B sub n small n and B sub n big N, so.
Yeah.
And that's why I think about it,
Yeah.
it doesn't tell you anything to say that, like, assuming B of n is divergent, it doesn't tell you anything that A of n is going to be less than that. But you know both facts, you know that it both has to be.
Yeah, it's not so
greater than
satisfying, but, yeah.
And since M and N are this constants, and B is constantly growing, you know that since A always has to be bigger than something that, like, B of n is making grow, that A of n also has to grow as fast as B of n is growing.
I mean, that's the best way that I can think about it is that these things grow together.
Okay. Yeah, that's.
You know, they're growing together, so like one may be 4 times as big or 10 times as big or 1,000 times as big, but there's still the basic pattern of growth or decline is the same.
You can just think of it as like.
That's the way I
it's
think
like
about it.
Sandwich between
Yeah.
those two terms, meaning it can't go down and it can't go up.
That's right. You
It has to
can't
go
like
up.
have all of a sudden one really shoots down. So this is what I want to show you with this. Because if I do the limit comparison test, and this is my A sub n, and this is my B sub n, I want to take the limit as n goes to infinity of over 1 over n,000, which is the same as this. And even though this is to 1,000th power, exponential growth is always eventually way faster than any polynomial. So the limit of this is 0. And I'm just telling you that what happens is this cannot shrink as fast as this is shrinking. They're not in tandem. As we go, you know, as n is increasing, one is dropping down so fast that we don't get this conclusion here. This conclusion. No?
That equals 0.
Yeah.
So if you get 0 or if
Eventually.
you get infinity,
Then they're too big apart.
so what does that conclude? Like what are we?
So then you can't use the test if you get 0
Oh, I
infinity.
see, okay.
Yeah, it's inconclusive. Just like the divergence test, if you get 0, it's inconclusive.
It's like comparing apples to oranges.
Yeah, it is. It is. So what I'd like to do, you guys, is show you that example, and I think that might clear some stuff up. This is the hard part, the conceptual part. Using it's not that hard.
One is on a ruler, you have like a variable to a constant, and one is exponential. And so it's like.
Do you guys have this written down in your notes? Can I erase? I'm going to erase. Or you can look online if you want to see it again. So, let's go back to our example. Oh no. And this is pretty much the end. It's hard.
But no matter. But no matter.
All right. So, I promise you guys it's way easier to use than it is to really, really get what's going on. I think this will clarify stuff. So we're going to go back to this example, 4n squared plus 1 over n to the 4th plus 1. So we said this converges. And I think Alice was really good to assign this b sub n to be n equals 1 to infinity over 4 over n squared. Okay, so this is going to be my b sub n series. I can choose a coefficient there, 4 over n squared. So I have my, and this is what I'm trying to prove. I'm trying to prove convergence. So I pick a series that's similar. It has to be very similar because they have to, I mean, as n gets bigger, the values of a sub n have to be very, very close. Even if you do n to the 5th, it won't work. You need this to be very, very similar. So remember what this says. This says, and in the book they say you let rho, that's like Greek letter. I can't draw very well. You guys know that Greek letter from physics? Okay, it's terrible. But in the book they use this. They say let rho equal the limit as n goes to infinity of a sub n over b sub n. And then, oh, I think I'll fit here if I do this. Then the limit of n goes to infinity of this. I mean, oopsie, I think you guys will see what's happening here. Divided by this, which is same as multiplying by the reciprocal. So can I just rewrite this to be times n squared over 4? Okay. Times n squared over 4. And now you just do the algebra here. Rho equals the limit as n goes to infinity of 4n to the 4th plus n squared 4n to the 4th plus 4. Now, if I hadn't chosen 4, if I had done 1 over n squared, this test still would have worked. So now this is a value between 0 and infinity. It's a finite number greater than 0. So this test worked. But only because as n gets infinitely large, these are almost the same thing. Indistinguishable. So that's the hitch with this limit comparison test. You really have to know that they're going to be almost the exact same thing as n gets really, really big. So this is one, and then your conclusion is thus, since what? Since I know I'm kind of in the corner here. I don't know if this is showing up. Since rho was greater than 0 and less than infinity, these two series behave similarly. So that's hard to do this way. Behave similarly. And this series does converge. And you've proved it. QED. Converge.
What if you were to pick instead of 1 over e to the n?
It doesn't work.
The limit, you get a limit of infinity.
Yeah, can't be infinity.
It has to be a numerical thing.
Yeah. For that exact reason. Those two series are too different. It's like, you know, it's this cliche, but like comparing apples and oranges, right? Okay, so I think I'm going to stop there, you guys. This is so important to practice. So I'm going to just kind of answer questions. Oh, that was half an hour.